Hello students, in the previous class we have seen the crystal field theory in octahedral complexes. Today let us discuss about crystal field theory in tetrahedral square planar complexes. So before going to this, let us revise previous topic. What is crystal field theory? Mainly what it explains. The crystal field theory mainly explains about geometry and splitting of d orbitals, and also here it is going to explain about the shapes and separation of the ligands and metals, mainly we can say. Okay, so but in octahedral complexes what we have seen there, so when ligands, generally in valence bond theory what happens, when ligand approaches it will give a shape and hybridization. But coming to in crystal field theory, when octahedral complexes, in octahedral, when ligand approaches, what happens here, it acting as a point charges. When it is in a free metal ion, there will be no change in energy, means same energy it is going to have. When ligand approaches, what happens, there will be some change in energy is going to happen. Okay, so then what happens, it is divided into two series, that is one is T2Z series, one is EZ series. Due to the electrostatic repulsions, electrostatic force of attraction, what happens there, EZ is having very high repulsion, means more energy, and T2Z is having less repulsion and less energy it is going to have. So that is nothing but octahedral. And coming to tetrahedral complexes now, so opposite to the octahedral complexes we can say. Why? Because here, so in tetrahedral complexes, so it mainly depends upon octahedral complexes only. So here the d elements, whatever it is there, means what here, the d orbitals is having same energy, which is known as degeneracy. Means what here, 5 d orbitals, that is dx square, y square, dz square, dxy, dyz and dzx. In octahedral what we say, EZ will be having between the axis, and dx square, dxy, dyz will be having along the axis. So because of that reason, it is having higher energy, it is lower energy. Now if you take here the lobes of dx square minus y square and dz square orbitals directly at the ligands for octahedral complexes. Now coming to tetrahedral complexes, what we have say here, 4 ligands located between the axis. Okay, so only 4 now. What is the shape of this one? Like this we are having tetrahedral shape. So what is the shape? Like this we are having now. Like this we are having, like diamond shape. So coming to here, this is a x, y, z axis. So when you are pointing this one, so they will come closer towards the z axis. So means what happens here, dx square minus y square and dz square orbitals, whatever it is there, these two orbitals will be having lower energy. Why? Because here dx square, dy square and dz square, these orbitals will be having lower energy, when dxy, dyz, dzx will be having the higher energy. This is opposite, means in this condition here we are having only 4 orbitals, and coming to here means 4 sides, and in octahedral what we are having 6. Okay, in tetrahedral we are having 4, but these are divided into dx square, y square, dz square. So this is EZ orbital, this is T2Z orbital. So this T2Z orbital will be having the higher energy, this one is going to have the lower energy. Now let us enter into diagram. So if you have been seeing the diagram, here we have taken tetrahedral complex. In this what happens, there will be less repulsions, more energy here, here high repulsions, less energy we are having. But when you compare these two, what happens here, here the T2Z can be written as T2 here in tetrahedral complexes, EZ can be written as E orbital, and this is having less energy, this is having more energy. Okay, This is in the tetrahedral and octahedral fields, just opposite to that one. So this one, what we can say, this is a barycenter or center of gravity. The energy difference, whatever it is, that one we are indicating delta naught, or we can say 10 dq we are saying. And coming to here it is divided with delta t. Okay, the barycenter is this energy, we call it as crystal field splitting energy, we can say, or crystal field stabilization energy also we can say. Why? Because here it determines about EZ orbital energy level and T2Z orbital energy levels. So here the crystal field splitting energy of octahedral complex is very large compared to the crystal field energy of the tetrahedral complexes here. Now coming to here, it is mainly depend upon what here, crystal field theory, electrostatic repulsion. Okay, so the orbitals closer to ligands. So the orbitals which are closer to ligands will be destabilized and there will be more energy. So in the same way here, for octahedral complexes, the overlapping is less. So that's why tetrahedral is very small. So this is about tetrahedral complex. Just opposite of the octahedral complexes, we can say it is a tetrahedral complexes. Now if you enter into square planar complexes, so it is one of the application of the octahedral complex, we can say. So up to now what we have told, in octahedral what happens, EZ and T2Z. EZ will be having more energy and T2Z will be having less energy, we have spoken. Okay, in tetrahedral what happens, this one is having more energy, this one is having less energy. But basing upon this application, basing upon octahedral complexes, we are going to get the square planar complex. So means what we can say here, what is the main theme of crystal field theory? To separate the metal ligand. So in this, when you apply again some force of attraction here, some force, some repulsions is going to happen again. So again it is giving higher energy, the dx square minus y square and dz square. So this will give what here, more energy. So because of that, what we can say here, it is known as square planar complex. That one we call it as trans ligands removed. Trans ligands is nothing but what here, opposite ligands are removed. So here we are separating the ligands on z axis, which is on z axis, that only we are separating on the ligand. Okay, why we are not separating on y axis? Why? Because the distribution of d electrons is only near the z axis. So if you see the structure of square planar, so this is the structure of square planar, right? So this is the structure of square planar. But here, which is similar to octahedral only, if you keep here ligand, so this is the octahedral structure. So but but when you take square planar, you are having only 4 ligands. Okay, so means what, which is similar to these 4 ligands is going to attract on z axis only. So you are having x axis, y axis, z axis. So what happens, the z axis, these orbitals will come closer towards the z axis. So because of that reason, what we can say, the z axis become more stable and x and y becomes here less stable. So whenever it is less stable, what happens, it is more complicated and it is separated into again higher energy. So by taking the octahedral only, we are going to split this splitting. Let us see the diagram here. This is the octahedral complex we are taking, which is denoted by delta. So when you here what happens, even though it is separated, it is having some energy. Okay, so then again when you apply some ligand, again when d orbitals are approaching, so what happening here, the dz orbitals are becoming closer here. See here, dyz dxz is becoming closer and dz square becoming closer, and here see here dxy dx square minus, it is becoming closer. So the difference between these, we can say what here? Crystal field splitting energy. Okay, so here this is more larger compared to this one. Why? Because we can easily separate the ligands in this molecule. So this is about crystal field splitting in octahedral, tetrahedral, square planar complexes. Okay. So now let us see John Teller distortion.